All right, welcome everybody to week 16, day 1. And there's no class next Tuesday. I might put up a video, recorded video, with some stuff for you guys to learn. But can you show an example comparing a 0 result versus unknown on the bus worksheet? Sure. So next week's the last week class. Week after that's finals week. The final will be, I don't know, I'll just put it up for a time period and you can take it whenever you want. Within that time period, we'll do the final review next Thursday. So that means we've got today's class and Thursday's class. Next Tuesday, like I said, I'll probably put up a video or something or other for you guys to learn. I think we've pretty much covered all the materials in this class. Let me just check my notes. It's because we're not doing projects, so we're actually done 2 weeks early. So normally do in-class time for that kind of stuff. Yeah, that's basically it. See if there's anything in the buses that we need to cover. I guess I could give you guys like a overview of yeah, that's everything. I guess I can give you an overview of how the projects would look if you were to do them, so you could at least see what breadboarding looks like, I guess, and see it from a distance. I don't know. So yeah, I guess we've actually kind of talked about this already. Well, I guess we'll go over that today. Okay, so first of all, let's talk about the Canvas worksheet. Did you guys have fun on the code tennis? Is there a simulation you could use maybe for breadboards? Yeah, we could do that. That could be a fun thing. And I kind of want to have you guys do maybe some data science. I don't know, just for the hell of it. Berkeley set us up with a free virtual machine with all these CPUs and things like that, and I have not used it at all this semester. And so they're like sending me surveys like, how do your students like it? I'm like, haven't touched it. So code tennis, hope you guys had fun with code tennis. My code, let's see if I hid the name. Okay. My code for function 1, O05 is the string passed in. With each character it reads from the input. It checks see if it's an O or no. If either is found, it'll overwrite both the O or O with O. Okay. Toadstool is immensely strong and immune to nearly any weapon when used properly. Nice. It's from the 4 venoms or the 4 deadly poisons. Let's do it. 5 deadly venoms, sorry. It's 5, not 4. Yeah. Also, Wu-Tang samples from it. You're not getting our data this time, Berkeley? GitHub banned you. Mm-hmm. It's funny. That's funny. All right. Yeah, I'll read through these. Oh my gosh. Let me pull this up on the other screen. That's an amazing first walk of Moses called. Oh my gosh. All right. So yeah, I'll go through these code tennis things. I expect to be amused by them. Did you guys get like why I was doing it though? Like getting experience making a library, using GitHub, pushing, pulling, linking. You know, it wasn't designed to murder anybody. Just yeah, just kind of running you through those steps. It was fun after you got banned. for having a sock puppet duplicate account. Use a VPN, man. VPN. It's all about. Subscribe to NordVPN on my channel and get 20% off for the first month. So I'm a YouTube streamer. ExpressVPN was on, but they just recognized like you had a cookie maybe or something like that from your other account. It's funny. Kearney Nord sponsor. Yeah, technically I do use NordVPN, but I am not a fan of it. I'm especially not a fan of their YouTube advertising. The only reason why I bought it was because I got like 2 years of access for like, I don't know, like $20 or something. Like it was like some ridiculous price. I was like, all right, that's actually a really good price. So I bought it, but I feel a little dirty for buying it. Raid Shadow Legends. That's these grayed out things. Your ultimate group project is doing Raid Shadow Legends. In assembly. Remember using Comic Sans as an automatic fail. So. Raycons, oh Lord, you guys are killing me. Audible. And on YouTube, I always get Ace Hardware ads. I don't know why. It's always Ace Hardware. Your barbecue something or other. It just makes me want to not go there, right? Like I'll just drive further to go to Home Depot. You know. Okay. All right, so the student asked on here, what happens if you have a disconnected linking dependency screwed me up hella hard, but I figured it out. Can we learn COBOL? No, I don't know COBOL. Comparing a 0 result versus unknown. So if you have if you try reading an unknown value, then if you're just looking at like a logic, you know, like a truth table, who knows what you'll get, right? But in real life, the answer depends on whether you're using what's called TTL or Cmos logic gates. So if you're reading TTL, it'll typically read as a true if you try reading from a floating gate. And Cmos, who knows what it'll give you. And so like TTL and the logic gate. These are just different designs of physical logic gates. And what house is that? Full of. Yeah, so it just depends on how like the the transistors are hooked up and things like that. But if you try reading from a disconnected TTL circuit, let's see, can I buy them? Shopping. Nope. Nope. Shopping. There we go. All right, so here is what a chip looks like. I guess we can talk a little bit about physical computing. So here's a chip, a little chip. And have you guys ever seen one of these things before, like just on its own, like not on a motherboard or something? So this here is a 9-input NAND function logic gate, TTL logic. So if you try reading from the output when there's no input, it'll give you a true, I guess. I mean, I guess it depends actually on how the NANDs are hooked up and stuff like that. But have you guys ever seen these things before? So, you know, this is 9 input, 1, 2, 3, 4, 5, 6, 7. So there's 14 pins, 9 inputs. What is the circuit diagram on that then? Details. You can't have, like if it's 9, is it like in groups of 3? What is the actual? I need to see the pinout diagram on this. Oh, right back where we were before. Great, cool, thank you. I hate these interstitial ads. They're so annoying. All right. SW 1802M. All right, so nope. You just give me a. I just want this circuit diagram, dude. Come on, seriously. Quad 2-input OR gate. Well, that wasn't at all what I was searching for, but all right, cool. Military grade, new. Okay. So this one also has 14 pins on it. And quad 2-input OR gate, so that at least tells me how the pins are lined up, right? So basically you're going to have pairs of pins and they're going to do an OR. So if you have a high voltage coming in on one of these pins, let's say 5 volts coming in on this pin, 5 volts coming in on this pin, if these are the input pins. I don't know the pinout diagram because why would they, show that? Cool. Can we get a... There's the... thank you. Right. We've moved on from that one. How do I open this in a new window? I guess I can do that. Okay, so here we got a pinout diagram for the NAND one that we were looking at before. Do you see this little divot here? When you look at a dip chip like this, there's a little divot, like that little semicircle cutout. That shows you which, because otherwise you don't know which one's pin 1 and which one's pin 14. Right? So the little divot shows you which way's up, so to speak, which way's north, And so when you're looking at it, let's see if I can go back to the previous one. Here we go. There we go. So there's the package, and so I need you. I'll snap you over here. Okay, here we go. So you can see the divots on this side, so it's actually rotated 180 degrees from this. But let's just pretend the divot's over here so I can just explain it without having to mentally do math and rotations. So this would be pin 1 if the divot was over here. This would be pin 1, pin 2, pin 3, goes to pin 7, and then it goes back like this. You deleted yours, Dolio. It's funny. I still have these from when I used to mess around with circuits. Yeah, circuits are fun. And it's something that we've unfortunately not been able to do in this class because of the pandemic, right? It's just, I kept trying to think of ways to do it, but like my experience with this class last year was, even though everybody knew each other in person and everybody had all the Raspberry Pis and all that stuff, just getting people together physically, for one thing, there's just a health risk, right? Like, can I morally and ethically ask 4 students to go into close proximity with each other to work on a project, right? So, yeah. Yeah, and it didn't happen also. Like, even the ones that did want to work together, it just became this logistical nightmare, and ordering parts became very complicated. Yeah, sorry, you guys just got screwed by the pandemic. So, yeah, maybe we'll do like a virtual breadboard or something like that. Anyhow, this is how it works. So let's say that this is a 5-volt chip, just for the sake of argument. And you've got a Raspberry Pi, like this. So the Raspberry Pi has these things called Gpio pins right here. And using, some of them are always on 5-volt output. That's high, that's true. Some of them are always on ground. There's a few special pins, but basically for about half these pins, you can control them in the software. So you write a program, and you can turn a pin on, and you can turn a pin off. And you can read the value from a pin. So you have to set up a pin as being either output, so the Raspberry Pi is going to control the voltage on it. I'm going to make you high no matter what, like a drug dealer. or I'm going to make you low no matter what, like a depressing person that you hang out with. Or it could be an input pin. And so the Raspberry Pi, rather than trying to set the voltage on it, will read the voltage on it. And so what you typically do is you get some sensors, and you wire the sensors. You get these little wires, and you attach them to the GPIO pin, and then your program will like read from the sensor, like there might be a temperature sensor, or a humidity sensor, or something like that, or an explosive gas sensor. It doesn't matter. There's sample code that comes with each of the sensors. And so you just run the sample code and verify that it works. You breathe on the humidity sensor and see that the humidity levels go up, and you wire the ultrasound sensor to it, and you move your hand in front of it, and it tells you how far away things are. And so we have these sensor kits. The school's spent thousands and thousands of dollars for you guys getting motors and sensors and all this kind of stuff for you. And so you read from an input. And you might say like, all right, when the temperature is too high, turn this fan on, or something like that. And if you want, you can run these things through an AND gate. So if the temperature is high and the humidity is high, then turn on a fan or something like that. You can either do that in software, or you can wire it up on the circuit itself using something like this. And so what you could do is, in this case it would be a NAND gate, is you would attach a wire to this pin. You attach a wire to this pin using a breadboard, which I should have. I'll go grab one of those in a second. And yeah, so basically you write software in the Raspberry Pi that reads from sensors and then turns things on physically in the real world. And I'm not going to do a double entendre with that. I've done enough of those already. So this pin here is going to always be ground. It's always going to be 0 volts. The one in the back over here is always going to be the VCC, which is 5 volts if you're on a 5-volt system. And otherwise, then these things are grouped into groups of 3 pins, 2 input, 1 output. And that's fairly typical. So if you have 5 volts here and 5 volts here, that's true. That's true. And then the output pin will be set to what? If you have a NAND. If you have true and true, what is true NANDed with true? What is true NANDed with true? How many volts output is that gonna send? 0 volts. Yeah. So this logic gate here will set that pin to be 0 volts. And then if that's attached to an LED or something like that, the LED will turn off. And then if you set 0 volts on one of these input pins, either of them, then the output pin here will be set to 5 volts, and the LED will turn on. And that's your basic hello world in the physical computing world, is basically just turning LEDs on and off. You don't have a console attached to this thing. You can't see out hello world, but you can pretty easily turn an LED on or off. And so you run your software and you write code that you think should turn an LED on, and okay, it turned on when I wanted to turn on, and it turned off when I wanted to turn off. All right, cool, good to go. And then once you do that, you just pull out the LED and you put on the whatever output device you want. If it's a motor, you usually can't power a motor through these sorts of weak sauce things. And so typically a motor will run through what's called a relay. And so a relay is like a remote switch. Like if I yelled at my daughter to turn the light off, and she came in and turned the light off, that'd be a relay. Ada, light on. She turns the light on. Ada, light off. Turn the light off. That's a relay. And so a relay, when you send a high voltage to a relay, the switch turns on. When you send a low voltage to the relay, the switch turns off. So what the hell does that do? It just, high volts creates high volts and low volts creates low volts. Well, it's because you can have a completely different power system. So rather than your Raspberry Pi trying to source enough power to power a motor, which will usually drain enough power that the Raspberry Pi reboots itself, it's quite common. If you hook a motor directly up to a Raspberry Pi, it just boop, and it turns off and turns back on again, and your program stops running. And so if you run it through a relay, you can have like a 9-volt battery pack attached to the relay, attached to the motor, attached back to the battery pack, and then your Raspberry Pi just turns the switch on. Hey, it's like it hits a switch over there, turn on, and then the motor spins up because it's powered by the battery pack. Okay, turn off, and that stops. And that is how you typically will do high load things like motors and things like that. Is that required to run the gate? Yeah. So this ground and this power, because imagine you send 0 volts in. There's no current flowing into the thing. But 0 volts and 0 volts is supposed to produce 5 volts. Where's the 5 volts coming from? It's not magic. Right? So this supplies power to the circuit. And so if you send 0 volts and 0 volts in here, then 5 volts will come out there. Okay? And you've got 4 different NAND gates running in parallel with each other. So you don't have to, when you buy a DIP chip like this, you don't, DIP stands for, I think, dual inline parallel. It's a package, actually. Chip, now loaded baked, what is this? Herbed, but, Gpio chocolate chips. No. Yeah, dual inline package, okay. My goodness. And so you can actually, oh, that's cool looking. That's cool. Yeah. And so a DIP chip has two rows of pins that you can attach wires to. And more commonly, you don't just have a wire attached to this thing, although you could. They're oftentimes soldered onto a motherboard. You guys see this? There's like a little bead of solder on these things. So this is probably machine soldered. They do things like splash solder onto the thing. And yeah, you can see there's solder connectors on this. So solder is like metal glue, if you want to think of it that way. It's conductive metal glue. And so if you have a motherboard that just has holes in it, then you can, when you're assembling the board, the first step will come through and just punch the resistors and the caps and the resistors, and this is a DIP switch here. And there's another DIP chip back over here, maybe it looks like. It'll first stick them all through the holes, and then it will usually do a splash of solder. And the areas that aren't supposed to be soldered might have some sort of like coating on them that will cause the solder to just fall off. And so the solder kind of sticks. It's at high temperatures, like at 300 degrees or something like that. It's molten, and then when it cools, they solidify. And so solder, if you heat it up, if you have like a heat gun, if you want to, like, let's say take this resistor off, you would apply heat to it. The solder would look solid, then it turns suddenly into a bead of metal. And you get a little like suction cup thing. You suck the solder out of it. Do the same to the other side, then you can pull the resistor off. And that's how electronics repair works in a lot of cases. Like if back in the day, people used to fix electronics instead of just throwing stuff away. And so like if your TV broke, you could take it into a TV repair shop and they would pop it open and they would diagnose the problem, like, oh, cap blew. And so they would just desolder the cap, pull it off, put a 5-cent new capacitor on it, repackage it, there you go, charge you $50 for the service, for the time, but the fixing is usually pretty easy. So solder wicks, solder wicks are also used. Same idea. You pull solder off the surface. Desoldering is annoying. Solder. Solder. It's not pronounced solder. Do you have a foyer in your house too? Foyer. Colonel. Yeah. There's different approaches to desoldering, and they're all kind of annoying. Desoldering things is it's a lot easier to solder things than desolder them. If you want to solder something, again, I would teach you guys this normally in class, but basically you could get like a perf board and looks kind of like this, solderable perf board. And so it's just a piece of silicon with some copper lined holes in it. And so if you want to permanently make a circuit, you could put like your DIP chip through there and then solder each one of the pins on. And you can put resistors through there and solder them on, and then run wires to connect the things, and you make a permanent circuit. Usually though, at least in this class, we do what's called breadboarding instead. So the breadboard looks like this. And it allows you to make circuits without soldering. So breadboards are really cool stuff. You typically will have your power supply attached to these vertical columns here. So you see the plus, that usually carries your hot. So like your 5 volts or whatever, if you're attached to a Raspberry Pi. I think Arduino's 3 volts out. Or are they 5 also? All official Arduinos run on 5 volts, but the coolest new sensors are 3.3, not 5. So you have to do a voltage divider. Let's see. How is it? Okay, so some of them do have 3 volts out. Okay. So anyway, so you could attach like 5 volts here and ground here. So like from the Raspberry Pi, somebody posted the pinout diagram on that. Let's see, copy link. So the Raspberry Pi, this would be not the original one, which is good. The original one actually had a smaller GPIO that didn't have as much on it. Okay, so the Raspberry Pi also has 3.3 and 5 volts as outputs. And there's a few special ones that don't really matter right now. Some of them are ground, some of them are power output. So what you could do is basically get a wire and attach a wire to that GPIO pin and run that wire to the breadboard. And so you attach a wire going from 5 volts on your Raspberry Pi to like this hole right here. And then you would run a wire from any of the ground wires, pin 9, pin 30, pin 34. You'd run a wire from that into that hole there. Actually, any hole. Because the way the breadboard is lined up is that you can't see it. And so, you know, the first time you work with a breadboard, you need somebody kind of to explain it to you. But basically, all of these holes in a vertical column here are all electronically connected. There's a piece of copper underneath the breadboard that's running vertically like this. And so if I put the 5 volt pin attached to my Raspberry Pi plugged into any of these holes in the left column here, then all of the holes in the left column here are supplied with 5 volts. And likewise, if I attach ground to any of the holes in the column here, all of the holes in the column here are now grounded. And you can actually have 3 volts on this one and ground on that one if you want. So you can have a 5 volt rail and a 3 volt rail, or you just do 5 volts on both of them, or just use one of the sides. It doesn't really matter. And so the first thing you do when you breadboard is you typically attach the power and ground to power and ground on the Raspberry Pi. The Raspberry Pi working as a power supply to your breadboard. Then these rows here, so these are columns, these two are 2 columns, and then all these numbers here are lined up in rows. So there's a piece of copper running underneath these holes horizontally. So if I have a pin attached at A1, it is electronically connected to B1, but it is not connected to A2. So all of these are horizontal rows, and they don't go across the Grand Canyon looking thing here, right? So there's 5 pins in a row, and they're all electronically connected to each other. So if I run a wire from the 5 volt rail into like A18 here, you see how that goes A, B, C, D, E. It's like Battleship, right? Battle sweep. If I run from any of the pins that are attached to 5 volts, if I run from any of them into, let's say, A19, then B19 is at 5 volts, C19 is at 5 volts, D19 is at 5 volts, and E19 is at 5 volts, but these are not. None of the ones on the right side of the Grand Canyon are at 5 volts. And so the Grand Canyon here is oftentimes just the right size for a dip switch, or a dual inline package to click across it. And so you can supply voltage to one of the pins, the pins of the breadboard dip. Like this. Yeah. So much fun doing this virtually. So yeah, it's usually just the right size for one of these dual inline package chips to click across the Grand Canyon. And so you can supply inputs to, you would usually run, where is the thing here? Yeah, you see where the divot is right here. And so if that one is VCC, you would run 5 volts connecting this to here on any of the 13s, and then the chip would be supplied with power. and then you'd run ground from any of the ground pins into any of the ones on 19 here, and then it'd be supplied with ground. And then maybe your Raspberry Pi has these GPIO pins. This. Any of these GPIO pins you can control through software to be high or low. And so let's say I set 19 and 21 both to be high, and I go from the pin into the breadboard. And I attach them to, I don't know, these, that pin and that pin there. Then if I send high volts from the Raspberry Pi, the chip is going to read in high volts. If I send low volts in from the Raspberry Pi, this is going to read low volts. And then the chip is going to send out on all of these pins horizontally the result of the NAND here. And then I could wire that into a motor or something like that. And so what's nice about a breadboard is that you don't need to solder anything. You click things in and you can just rip them out, and when you put them in, they make a nice kind of, if you have a really cheap breadboard, like it can get really annoying. You got your wire and you're trying to like put it in, and if the breadboard is misaligned, then the holes don't line up right, and you're like trying to like jam it in and like kind of work it. Like really cheap breadboards, oftentimes the holes in the copper backplate don't line up with each other, and then you throw the breadboard away and buy a slightly more expensive one. Or you can like work on it and try and make it work. But when all goes right, you take a copper wire and you just put it into the hole, and then it just clicks in like that, and then that wire is attached horizontally to all the other things. And so if you want to, so rather than needing to glue two wires together using solder, what you do is you take one wire and put it into, let's say you put it into hole B30 right here. So you have one wire coming in like this, the other wire is attached somewhere else. And then you get another wire and click it into E30. Those two wires are now connected. And so rather than needing to glue two wires together, you just put one wire into B30, you put another wire into E30, and then because there's a copper backplate running beneath them, they're now electrically connected, and current will flow between them. And so it allows you to very quickly prototype and click things in and pull things out. And it's a lot of fun, honestly. It's a lot of fun. And I'm kind of sad you guys don't get to do it. So let's see, copy link. Yeah, this shows the wiring of a breadboard. Okay. So yeah, I don't think there's enough JPEG on this image, Julio. I think we need to amp this up a little bit. There we go. That's much better. There we go. There. That's our circuit diagram right there for. All right. Yeah, and so basically all of these 5 pins here. This is sort of what the underside of the breadboard looks like. If you were to take the plastic shell off, you would see that there's strips of copper underneath these 5 pins. So all 5 of those pins are electronically connected together, and these vertical rails are all connected together. But these rails are separate from these rails. Right? Does that make sense to you guys? You can't use where you put the integrated circuits unless you're weird. Yeah. So you click that in the middle there, and then you can attach wires to any of the 4 pins to the left of the integrated circuit and pins on the right side. And yeah, so that's how it's sort of electronically hooked up. And let me go get a project my daughter did. I'll be right back. Let me pause the recording. I'll show you guys kind of what this looks like. All right. So every year my daughter does a Raspberry Pi project. She's been doing so since she was about 3 years old or so when Richard Stallman came out. Literally the only time I saw him impressed was when my daughter was like breadboarding when she was 3 years old, and she was like wiring up a motor, and she attached a ballerina to this motor and was causing it to spin around, and she hit a button. And he was like, "How old is she?" 3. Like, oh, nice. Otherwise, the dude is completely like unimpressed by everything. All right. Was it sneeze recorded? I don't think so. I unpaused it after I sneezed. So this project is actually really simple. This is actually probably the simplest project she's done, but I don't know where her fish diorama is. And so she built a model of a camel. It's a laser cut project. Like, she didn't design this herself. She just had to assemble it. It's pretty simple. But she made a poster on the different features of camels. She did a project on camels. And so what she did was she just glued, actually that's electrical tape. So she attached different LEDs to the camel. And so there's different buttons for the lips, which are adapted for eating cacti. The humps, obviously, for water, which is of course a blue LED. The hide, which is desert colored, things like that. And then when you push the thing on the poster, there's a button and it says, this is the hide, this is the humps, this is the lips, things like that. So, really, really basic stuff. Like I said, this is the easiest project she's done, but the kids liked it. You have a diorama, you hit a button, and things turn on. It's like, they have these like science museums, right, where you just hit a button, it lights up something, or you're at a history museum, click here and it highlights the Amazon River or something like that. How much JPEG are you guys adding to that? It's amazing. So the wiring looks like this. So I've got the Raspberry Pi here. The black box is the Raspberry Pi. You can see dangling at the bottom in front of my arm is the power adapter that runs into the wall. And then the Raspberry Pi has the Gpio pins. Has the Gpio pins right there. I'm wiggling it. See them? They're running out into the breadboard. We normally keep that closed up so that we don't get water spilled on it and stuff like that. And so over here we have, see if these wires aren't coming out. Then over here we've got the actual breadboard. Okay, and so it looks like a bit of a mess, but basically we've just got 3 very simple circuits. We've got plug these back in. Can you make the camera bigger? The camera is one size. I can try holding it up a little closer there. Okay. It's about as far as this thing will reach. Okay, so the yellow wire is running out of the 5 volts on the Raspberry Pi, and it is attached to the the red. Okay, the ground is the brown wire. No, let's see, the green wire, right there in the bottom right corner. The green wire that's attached to the ground rail. So that's the ground coming out of the Raspberry Pi, and then I guess that's it. I guess we're just using the Raspberry Pi as a power supply. We're not even doing no programming on it this year. Last year we had actual programming. So you can see I've got a bunch of little jumper cables here, like the little blue one here where I'm tapping. There. That's running from the hot rail into row 28 right here. And that is attached to this button here. And then on the other side of the button, I've got a resistor right here. and the output of that goes into an LED. And I've repeated that circuit 3 times. And then at the very end of the LED, there is a wire running back into ground here. That completes the circuit. So by default, the circuit is not open, like it's not closed rather, it's open. But if I press the button, then it closes the circuit. Current flows from the hot rail through the blue wire into the button, into the resistor, into the LED, into the ground, completing the circuit, and the LED turns on. You have to have a resistor or the LED will explode in a little puff of smoke. First time I taught this class, the student wired up an LED directly to 5 volts and hit the button. It popped, a little puff of smoke. He's like, oh, that didn't seem to work right. Pulls it out, puts another one in, hits the button, it explodes, pulls it out, puts another one in, it explodes. I'm like, dude, you got 5 for the year. You've made an electric chair for LEDs, dude. Stop. You need to put a resistor on that. So that's it. So it's a very simple circuit. Yeah, unplug it. But the kids loved it. The teacher loved it, of course. You don't see too much breadboarding in a 3rd grade class, I guess. So you can see it's just the same circuit repeated 3 times. Really trivial. You see the blue, the red, white, and blue are just jumping the 5 volts over from the power rail up top here. You see that? The yellow wire is attached to 5 volts on the Raspberry Pi, so it supplies that top, the red rail up top here with 5 volts. And then the blue, the red, and the white just carry that over to the momentary push button switch. And then the output pin of the momentary push button switch is a resistor, and that attaches via wires to the camel. And then the output of those LEDs goes into the bottom rail here where my thumb is. And so you can see all 3 of those LEDs are hooked up to the ground rail, which goes back into the Raspberry Pi, completing the circuit. And thus, when you push the button, the light turns on. No pull-down resistors. So the Raspberry Pi, all the pins on the Raspberry Pi have either pull-up or pull-down resistors on it. So you don't need to do it yourself. And you have to look up which ones are pull-up and which ones are pull-down. So when you turn it on, it doesn't... That was a problem some of the students had, right? They attach their motor to a pull-up resistor. And so when they turn the Raspberry Pi on before the program runs, it's like, on! And their thing starts spinning like this. And then when the program boots up, because I taught students how to launch a program automatically at boot, but it takes a while for Linux to boot because Raspberry Pis run Linux. GNU/Linux, as I'm taking to call it these days. And so the fan would sit there and then it would boot and turn off. And so I had to teach them about pull-up and pull-down resistors that way. So when it's not on, what do you want it to default to? 5 volts or 0 volts? And you have to look up the tech specs for which one is which. So let me show you. Yeah, see, even this doesn't tell you, I think. Yeah. Pull up, pull down. Doesn't say. Let me show you her aquarium. I have her looking for it right now. She might bring it in or she might not. Let's see if I can find it. Posts. Okay. All right. So here is 2nd grade Ada. We have, so your diorama is coming along nicely. We have a big nose. We have a servo. What is the servo going to be used for?
It's going to be motor.
Faster bedtime.
That's 9.
10 o'clock.
Oh. That's so 5.
So, what are we going to use that servo motor for?
To use the fish to go to that.
Okay, so we're going to glue a fish to it or something? And what about the LEDs? What did we do with the LEDs today?
The LEDs we programmed them. We made them light up.
And what else? You guys hear that? Actually, I should have asked. Can you hear what she's saying there? Or is the audio not coming through? Very quietly. Barely. Alright, let me switch the screen over. Change windows to Facebook. Right. So basically, after she goofs around a little bit, I asked her what are the servos for? And so you can see how the servo is kind of wiggling like that back and forth. What we did was we attached a fish to it. So we punched a hole in the back of this shoebox, ran a servo to it. Servo motors don't spin. I mean, I guess they can technically. Use that servo motor for?
Use the fish to go like that.
Okay. So we're gonna glue a fish to it or something.
Yeah.
So you've got kind of two main categories of motors. You got your standard DC motor, where you apply voltage and things spins, and the higher the voltage, the faster it spins. And so a servo motor technically can spin like that, but usually you use it when you need precise controls. Like if you have, like your car, if you have the speedometer on your car, right? That could be done using a servo motor. So you say, set the angle to be 60 degrees, set the angle to be 90 degrees, set the angle to be 120 degrees. They're braking, set the angle back down to 0. And so servo motor can be used to very precisely control the angle of something. Stepper motors have similar purposes. They count how many clicks they make. And so you can get very precise controls on things using stepper motors and servo motors. And in this case, we programmed it so that the servo motor would kind of go like this, like a fish. And so if you look at the servo motor as she's holding it, we're trying to simulate like a sinusoidal motion of like a fish. What are we going to use that servo motor for?
Use the fish to go like that.
Okay. So we're going to glue a fish to it or something?
Yeah.
And what about the LEDs? Did you see it wiggling in the background there?
What did we do with the LEDs today? The LEDs we programmed them. We made them light up.
And what else?
We also make the motor work.
Yeah, but do the LEDs stay the same brightness or do they change?
They change a little bit.
They change a little bit, yeah. So do you see how the LEDs are kind of glowing a little brighter and a little dimmer? Rewind. Do the LEDs stay the same brightness or do they change?
They change a little bit.
They change a little bit, yeah. At first they changed a lot, but then how did you like them?
They changed a little bit.
Just a little bit. Stay for you, huh?
Mm-hmm.
Okay, all set. So that was the basic design of it. So it's just a servo motor and a bunch of LEDs, and we set it up so the LEDs would increase and decrease in brightness. And so it'd create like this underwater effect, like if you've ever gone scuba diving or something like that, it's got this kind of effect underwater. So we wired up the shoebox with these LEDs, and then we punched a hole through for the servo motor, attached a fish to it on the other side, so the fish would sit there and swim like this. And yeah, it worked out quite nicely. Here she is wiring the thing. That's her physical non-electronic diorama prior to electrifying it. So she did research on different kinds of coral reefs and things like that. And then, so your diorama is coming along nicely. And then we used an Arduino for that instead of a Raspberry Pi. Johnson is like, I'm disappointed in the Arduino. She should be able to handle Pi projects in CSI45. And then this is what it looked like when we finished. 4 LEDs that dim and brighten. 2 on top and 2 in the back. You see the wiring up here? And it's got a servo motor that has a fishy tilt up and down according to the sign of time. It's got a number of real shells, sand, glue, informative displays of what all the different things are. It's got some pipe cleaner kelp, seaweed.
Can you give me some water, please?
I'll get you some water, girl. I'm sure looking at all these fishes make you thirsty. On the back, we Okay, so here's the wiring on the back. So a lot of breadboards actually have a peel-off sticker, so you can actually slap them on things like this. That's what it's for. You know, I guess you've kind of lost the breadboard at that point, but they're super cheap. And so I just slapped it on the back of the shoebox and then wired it up to the Arduino. Again, you got hot, you got ground, and you got the wires going out to resistors and LEDs, and then another set going over to the servo motor. Now, normally an LED is either on or it's off. And so how do you get something to dim? There's a couple different ways you can do it.
Got a Arduino, a breadboard, and some wiring to make it all work. It was a lot of fun.
Okay. So what is this? Interesting.
All right. So you got your snap circuits in today. Tell me about the circuit. I just modified it, so you might notice something different.
You should know this. I just hotwired.
You hotwired something, okay.
I didn't hotwire a car. I hotwired this.
So you're bypassing a switch. You're bypassing a switch, okay?
Oh, didn't expect that to happen.
I just added the light there.
Yeah. He replaced this thing.
I replaced a wire with an
I was
LED.
about to short the circuit.
Do it. Oh, no.
Short the circuit.
Yeah, don't short the circuit, but you can bypass the switch. Pretty cool, huh? Is the fan spinning slower now?
Yeah.
Is the fan spinning slower now that there's a light on the circuit, or do you think it's about the same?
About the same.
Because
Because
the LED doesn't really consume much electricity, does it?
yeah, yeah. How come?
LEDs don't use very much power at all, so it is going to drain a little bit, and the fan will turn a little bit slower. I don't know if you'll be able to detect.
I'll close out of that and switch the screen back over here so you guys can see again. Okay, so yeah, just doing little projects like that. Like if a 6-year-old and a 7-year-old can do that, or an 8-year-old can do that, you guys should be able to do it. So if you want to get into that kind of stuff, what we bought for the school, oh my gosh, is we bought Extreme Kit. I don't know, depends how much money you want to spend, I guess. But Canakit makes a kind of an all-in-one package. Like if you want to go hardcore, like 128 gigs is usually way more than you need. And so it comes with a Pi, it comes with a case, it comes with a fan for the heatsink, power supply, switch, Raspberry Pi 4 with the 8 gig model. USB adapter for the micro SD cards, so you can load things up on it from your PC. And it comes with was it DisplayPort or HDMI adapters and things like that? It's HDMI. I think it has the new Raspberry Pis have a micro HDMI adapter or port, so it has a micro HDMI to HDMI adapter there. And then that's kind of on the pricey end. Like you can get much cheaper editions like this. Yeah, just a heat sink, it's fine. The Raspberry Pi 3, which is also fine, $60. I wouldn't go below Raspberry Pi 3 though. The Raspberry Pi 2s don't have Wi-Fi built into them, and so it's kind of irritating. You have to get a Wi-Fi dongle and plug it in, and it's kind of annoying. So if you're going budget, I would go with probably this one here. And so $50 gets you a full computer. Does it come with a SD card? SD card. Does it come with an SD card? If it doesn't, then I'd probably get one of the ones that has an SD card on it, because they preload it with all the software you need, which is nice. Otherwise, you'd have to go to Ban noobs. And so you'd have to go to raspberrypi.org, go there, download it, get a imager. It's not the end of the world, but you'd have to still buy the SD card and the adapter, and it's just kind of easier to just get it preloaded like that. So just search for one of the kits that have an SD card with it, and don't get a Pi Zero. Those things are not really designed for general purpose computing. But yeah, this one comes with a 16 gig. Somewhere in that range. Yeah, $80. That'll do you. And then you can just hook up your Raspberry Pi to your monitor. You just plug any HDMI monitor, you plug it in, and you get a USB keyboard, USB mouse, plug it in. I use it on my TV, so when I'm working on my Raspberry Pi, I'll just plug my Raspberry Pi into the HDMI input of my TV, get one of my spare USB keyboards and mice that I've just kind of lying around here. Over the years, techie people build up just tech closets of stuff. If you want USB cables, HDMI cables, I've just got in my closet back there shelves of adapters and cables and devices and things like that. And so I just plug in a random mouse and a keyboard to it, and then it boots up, and then you've got a working Linux box, and you guys can learn how to run your own Linux box. So run Pi-hole in yours, very effective in blocking ad networks wide. Yeah, that's a really good idea. Pi-hole's great. You can also do like arcades, like and so you can actually literally build your own arcade machine and things like that. You can use MAME to emulate the old games, and you get a bunch of buttons, and you can wire everything up. I've had students do this as class projects before. It's kind of fun. And at the end of the day, you end up with a you know, we'd play Tekken on it and stuff like that. So okay. Yeah, you can MAME. I don't know if you guys have ever used MAME before. It will emulate many different games. So you just run MAME on your Raspberry Pi, hook up some controllers to it, and you can have, and if you build a cabinet, like you can have something that looks exactly like an arcade machine, where you can pick from thousands of games and play them. It's pretty fun. Okay, so how do you make the LEDs glow brighter and dimmer? There's something called PWM. Okay, and PWM stands for pulse width modification. Not pone. Old Game Boy, yeah. Pulse width modulation. And so what you can do is it's like, imagine if you turn a switch on and off really fast, right? What happens is that rather than the voltage being 5 volts and 0 volts, if you turn it on and off really fast, it'll effectively be like 2.5 volts, right? So if you turn it on and turn it off, 50% on, 50% off, and you do it really fast, then from the LED's perspective, it's not getting 5 volts as input, it's getting 2.5 volts as input. And so PWM pins on the Raspberry Pi can be used to control. It's sort of like an analog out. It's not exactly an analog out. It doesn't actually do continuous voltage outs, but it just flips the voltage on and off fast enough that you can get 90%, 80%, 10%, whatever you want. Whatever the duty cycle is the percentage of the voltage that you get. And so by doing that, I would send to the PWM pin, turn on 100% of the time, down to 10%, up to 100%. And by playing with the sines and cosines and things like that, we were able to create this cool breathing effect of the LEDs. And having, I think we actually wired them up separately. And so the LEDs would kind of go like this across the tank, making it look like it was underwater. It's a really neat effect. The PWM is also used to control the servo motors. What percentage it's on controls whether the servo motor is at 0% or at 100%. And so if you turn it on and off half the time, it will be at 50%. And there's different ways you can wire them, but that's the general idea. And yeah, servos. And so yeah. And so PWM, the Raspberry Pi has a couple PWM pins. And if you need more analog outs than that, you're kind of hosed. And so there's these things called, like if you want a servo hat. So if you want, it's not what I want. So if you want to control multiple servo motors, you need to have multiple PWM outputs, and there's just not enough from the Raspberry Pi. And so you buy this thing called a servo hat, and you attach the servo hat to the Pi. There are these, where are they? Where are you at? No. So around here, there's a serial, a couple of the pins are used for serial connections. And that will send signals to the hat saying, set servo 1 to 75%, set servo 2 to be 10%, set servo 3. And so it'll send a serial transmission to the hat. And then the hat, which is separately powered, which is also good, because again, drawing power from the Pi itself can cause its voltage to dip enough that it reboots. So you have the servo hat powered separately, and then it will have, it'll do the PWM to control the servos for, how many? 16? So you have up to 16 different servos attached to it. So like, let's say you're making an arcade game or something like that, or let's say you're making a pinball game. Have any of you guys actually played on a real pinball machine? Not like the video game version of pinball, but like actually a real pinball machine in real life. I have a friend that's like super into pinball. Like there's apparently these services where you can like rent pinball machines, and every month they'll swap out your pinball machine. And so you get to play on the Iron Maiden pinball machine for a month and learn it and master it, and then they switch it out for the Elvira one or something, I don't know. And so pinball machines are really, here comes a copyright strike. Are really, let's see if we can just see one. There's a lot of different things that move around. You see all these different lights that are lighting up, right? So you've got some controller is turning these lights on and off and causing some to flash and some to pulse and waves of lights coming on and off. And when you hit a button, there's a servo. You see the flippers move like that. And then when you hit bumpers like that, they activate. Yeah. So you could, in fact, I've had students make pinball machines before in class using something like that, and yeah, it doesn't really break the bank, You're for this class, you're given a Pi and you're given servo motors and things like that, but students would buy additional components as needed. They probably should put in for like a class set of these as well, just because they're so useful. Nickel Arcade, yeah. Mm-hmm. Yeah. So, are those open again? This is pandemic, All right, so let's learn some basics of circuits. I guess we're just doing physical computing today. PowerPoint presentation, yeah, it was related actually. So if you and it's related to the bus too. If you try reading from a floating pin, if nothing's attached to the bus, what do you read? And the answer depends, right? So for your worksheet, you're just supposed to put down X. Like, who knows? Okay. But there are these things called pull down and pull up resistors that if the wire is floating, in other words, there's nothing attached to the input, right, then it will default to 5 volt or it'll default to 0 volt. So it'll look something like this. So if the switch is detached, then this would default to 5 volts, right? And if you attach the switch, then whatever, in this case, it'll be ground, right? So this resistor is usually a pretty big resistor, so current's not really flowing through here, but it will keep a high volt for the logic gate. So the logic gate will keep reading a high voltage. PWM, yep. So, so if you turn your pin high to 5 volts half the time and a low to 0 volts half the time, it'll effectively be 2.5 volts. All right, classes in memory. We kind of talked about this before. So this guy's at offset 0, this guy's at offset 4 bytes, this guy's at offset 8 bytes or something like that. So if your object is at address FF00, the int will be at address FF00. The float is going to be at FF04 because it's 4 bytes later, and the pointer is going to be at FF08 because it's 8 bytes later on a 32-bit system. I've already talked about this before. And so basically you read from objects, class objects, just like you read from arrays. Classes are really just heterogeneous arrays. Classes are just arrays that can have different types, right? If you're reading from an array of integers, everything's an integer, right? But a class, this is an array of an int, a float, and a pointer. So you just read from them just like you're reading from an array, and that's it. All right, so I don't know. Let's see if we can find a virtual breadboard. I do want you guys to get some experience with this prior to going off to a real college. Remotified lab. Virtual breadboard app. Is this gonna cost money? Fine. Let's try this out. Get offers in-app purchases. Just what I want. It's exactly what I wanted. How did you know, Microsoft? I love some in-app purchases. Tinkercad, yeah, I've used Tinkercad before. Let's try this out real fast. 3 stars out of 5, you know it's good. Yeah, Tinkercad is run by Autodesk, which is the company that makes, you know, some of the best CAD. CAD stands for Computer Assisted Design in the world. Let's see if my account still exists. Sign in, email username. There you go. Tinkercad lesson plans. Maybe that could be your next homework assignment. 3D design, circuits. Okay. Tinker with circuits on Tinkercad. Let's try circuits. Here's a virtual breadboard over here. Let's see. Who do we like better? So this isn't a breadboard, you just wire things up. Okay, we got a breadboard. Alright. Okay. Alright, not bad, not bad. Let's check out this virtual breadboard thing. No, I don't want to buy anything. Don't show the welcome screen. So much garbage on the screen. Okay. Breadboard. Avatar Uno. Alright, let's give you some wiring. How do we wire this? Wires, okay. Goodish. Alright, so let's wire some stuff up. Let's see. What do we got here? 5 volts. Where's our 5 volts? LED. Power on. I don't know. Never used this tool before. Let's go check out Tinkercad. Close, yeah. You guys understand soldering? Like with breadboards, you don't need to solder, but with but if you want, you can solder things together and then make them permanently attach to each other. Okay, metal glue. Okay, start simulation. I know light turns on. Can we test? Do we have a multimeter? Can we test what the voltages are here? Click. Can I click? No. View. Let's add a momentary push button switch to this. Alright, yeah, that works. So when I click on the button, the light turns on. Okay, it's a 220 resistor here. Do you guys know that you can tell the resistance of a resistor by looking at the colors on it? This one looks much easier to use. Yeah, I think I'll give you guys an assignment on this, like build a little circuit or something using Tinkercad. I think that's fair. So, what kind of project would you guys like to do? This is a 3 volt. Interesting. What kind of little project would you guys like to do? So if you want to read a resistor, the first thing you have to do is you have to look at where the metal band is. There's going to be basically silver or gold here on the right hand side, and that shows you which way to read, left to right. And so you always put the that is the right side. So this would be red, 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 brown. And the gold just means the tolerance of it. They're all basically gold these days. Where'd you go? Not you. You. Okay. So the each of the digits of the resistance is indicated by color. And the first two are the significant digits, and the third one is the power of 10 that it represents. And so if you had a brown, black, red, brown is the number 1, black is the number 0, and red indicates times 100, essentially, 10 to the second power. And so this would be 10 times 10 to the second power, or 1,000. So this is 1,000 ohms. Okay. The 220 that we had over there was red, so 2, 2. And then what power of 10 for the third one? 10. So 2 times 10, 220. Okay. So a red, brown is a 220 ohm resistor. A yellow resistor would be 440,000 ohms, right? So 4. The first two colors are the significant digits, and then the third one is the power of 10 it is. So if you have a yellow, it'd be 44 times 10K. So 440,000 ohms. Okay. Wouldn't it be 100? 10, no, for this one? This is 10 times 100. So it's 10 times 100. Okay. You could have alternatively done this maybe with like black, brown, and orange, right? 1 times 1K, I guess. Does that make sense to you guys? So, there's a little bit of electrical engineering know-how for you all. All of you are going to have to do this at some point in your careers. Probably most colleges that I'm aware of have some sort of electrical engineering classes required for computer science majors. So you're not totally ignorant and totally useless when it comes to the real world, right? Like after taking my class, one of my students went to Fresno State, and they do these giant breadboards and things like that. I'll probably pull up a picture of it. Yeah, those are really complicated breadboard thing. He sent it to me, really proud of what he had done. And I was like, cool, that's awesome, you know. So at my college, UC San Diego, we have to take 2 semesters of electrical engineering. And they were fun classes. I really enjoyed them. Learning about the real world instead of the sort of idealized software world where we live up in the clouds and descend from reality every once in a while. And we have a power outage or something, you know. We operate in a reified state of theory and math, and the electrical engineers have to deal with things like quantum tunneling effects, you know, and electrons teleporting through physical barriers and things like that. So learning how to wire things. Mr. Bell, if you guys remember him, he popped the front of his temperature, his thermostat at home. And so if you're ever taken a thermostat off, it's just a couple wires coming out, right? And so what he did was he hooked up his Raspberry Pi to the wires coming out of the wall and just take the thermostat off, pull the wires out. He got these wires, and then he had his Raspberry Pi control the temperature in his house. So he had a temperature sensor, humidity sensor. Probably that's it. And then the Raspberry Pi would just sit there and be like, oh, yeah, it's getting a little warm in here. It's getting a little humid in here. You run the AC, you know. And so that was easy project to do with just like a really basic understanding of this kind of stuff. What kinds of sensors are there? Well, this is the second half of what I was going to show you on Amazon. So the first thing, if you guys want to get into this stuff yourself, you can buy the Cana kit, and then there's also a lot of sensor kits and motor kits and things like that. The ones that I use is the Sunfounder sensor kit. It's not the cheapest by any means, but they have really good documentation, and they have really good source code, and that I like. Whenever I want to make something work, I always start by just downloading the sample source code and hooking everything up and seeing if it works, you know. And you know, here is this one? No, it's close enough, I guess. And so, like, you hook up a sound sensor, right? And you yell at your computer, ah! And you see the numbers go up, you go quiet, numbers go down. Photoresistor, put your hand over it, see the numbers go up, take it off, the numbers go down, or vice versa. Some photoresistors work in opposite of light, some work proportional to light. A potentiometer is like a knob, so you can turn the knob and it will read how far turned the knob is. And so this is very useful if you have like a volume control, right? So you turn the knob and you're like, how much is the knob turned? And you can set the volume on your device based on that. And so flame sensor, have I had students use a flame sensor before? Yes, I have. Yes, I have. Have I had them use the explosive gas sensor before? Yes, I have. Joystick PS2 module, so it's a thumbstick, so you can program, you know, robots and things like that to control it with this. And it just reads for this one. I believe it reads the vertical axis and the horizontal axis separately, and I believe you can click it down. So I believe that gets read. So the sample source code. The pot meter. Yeah, we call these things pots, the potentiometers. Humiture is both humidity and temperature. Infrared receiver, I think it comes with it comes with a remote control there. And so you can send IR commands that the IR receiver will receive. And so you can sit there and have, you know, pie hole activate. Why not? Why not? So we've got, all the Sunfounder sensor kit. Oh yeah. So if you guys are curious about how to turn on a Gpio pin using assembly, you guys remember how I told you about memory mapping a week or two ago? How you can memory map chunks of the system's physical address space into your address space? The GPIO pins all live at a certain memory address. And it changed between the Pi 1 and the Pi 2. But basically you just load, you just map that into your current address space, and then you can do things like this to turn pins on, turn pins off. And or you can use the GPIO library. Let's see, read all. That's it. Sudo. And I will. Is that not installed correctly? No. Yeah, I mean, you could do something as simple as saying, like, turn pin 5 on if you want. Yeah. So, the sensor kit, Sunfounder sensor kit, it comes with source code for all the different sensors, right? So if you want to see how the Hall sensor works, it's the first option there. Hall sensors are used for magnetism, as are read sensors. So switch Hall, and so what this will do is, this is a program. You know, this is what it looks like when you guys do physical computing, which you're gonna miss out on. But seriously, on Discord, think about what kind of wiring you'd like to do, because I'm gonna give you just a little wiring assignment virtually, so you guys can at least have some vague familiarity with it before you move on in this world. to greater things, more professional professors, more professorial professors. All right, let's switch all, and it's going to give me a linker error if I do this. There we go. And so I need to link in wiring pi. Nope. Link in wiring pi. Dash L wiring capital P pi. There we go. Yeah. Okay, so if we run it, cannot access the GPIO. Try running it with sudo. Yeah, sure. That's sudo. Get that out. So right now, the program is trying to read from the GPIO pin. Obviously, nothing is attached, so nothing's happening. But that's basically the process you go through. I should probably make a note of that in the source code. Pile. I have to look that up every time. And so, anyhow, so what you do is you just include the wiring pi library, and you call setup. That gets everything initialized. You specify which pins you want to play with. These are over here. And so the pin number for wiring pi is actually not the physical pin number, but the GPIO pin numbers. I think that's actually, there's actually wiring pi pin. These systems are numbered multiple ways, which is super annoying. So physical pin 3 is GPIO pin 2, which is wiring pi 8. So wiring pi 0 is physical pin 11 and GPIO pin 17. So this one's going to be messing with these two pins here. And if you think that's confusing, yeah, it is. It is, absolutely. So they have different numbering systems. So anyhow, so we're going to be reading from this pin, and we're going to be writing to that pin. So it's going to read, it's going to do a digital read from that pin, pauses for a little bit of time, and reads from the pin, and it's going to read from the pin, and if it ever and then it will write to this pin, let's see, while not digital read. So until it reads something from the pin, it'll infinite loop. That's why it wasn't doing anything. And then it's going to write to the LED pin the true, I guess. Yeah. Okay. So it'll basically just sit there and do nothing until you put a magnetic material near it. Then it will activate and print that. And then if you take it away, it'll go back into here. So as long as it's reading false, it falls into here. Then it's going to say while you're reading false, once you read true, by putting a magnetic material near it, then it will turn the LED on, and once you take it away again, then it'll jump back up here. So that's all it really takes to do stuff. Tilt switch. Again, not doing anything because I don't have anything attached to my Raspberry Pi. Let's take a look at this. So again, it uses these pins. You can change which pins. If you're going to be using multiple sensors, you obviously need to change which pins you're using. So it tries setting up wiring pi. It sets up the pin for input from reading from the sensor. It sets up this pin for output to write to the LED. And then it'll just sit there and read over and over again. And see, if it reads a false, then it turns off the LED. If it reads a true, it turns on the LED. So basically, it just sits there in an infinite loop, reading over and over again from the sensor. And if you tilt the sensor this way, a little ball falls down, current flows, reads a true. The LED will turn on. You tilt it this way, ball rolls back, no current flows, it reads a false, the LED turns off. And that's all it really takes to make a simple system. And in general, when you do physical computing, you've got sensors that read things from the real world, you've got a controller that does the logic, and then you've got things out in the real world, actuators that turn on lights or turn on motors or things like that. And that's it. Like, I mean, you guys can look at this. It's not really very hard, I don't think. You know, so, any questions about that? I know you can't do it, and so it's all sort of theoretical, but
what does green mean?
what is what?
What does green mean?
What does green mean? It means he's a TA or something. He's a tutor. Yeah. Is that going to be our next assignment? No, because you don't have any Raspberry Pis. So, no. Normally it would be. Sorry. Now your next assignment will be going on to Tinkercad and making a circuit of some sort. The virtual thing, yeah. Mm-hmm. Yeah. So yeah, I like Sunfender. They're not cheap. There are cheaper kits out there, but the fact they have source code for everything makes it really nice. They don't expect you to figure out how to, use the things just cold. Maybe if you're a super cool person, you could, that an ultrasound sensor requires a high volt and then a pause and then a read and so it's got source code for all these things. That red thing there is a T adapter, and so the GPIO pins from the Raspberry Pi, you see that rainbow cable down in the center? You can attach that to that whole set of GPIO pins, and you run the other end of that cable into that T adapter, and then the T adapter clicks into your breadboard, and then the breadboard is now directly hooked up to your Raspberry Pi, and you can individually turn on this row or this row. Most T adapters also have power coming down the corners. This one doesn't. I don't know why. The CanaKit, I think, comes with one that has power supplies as well. And so with this, you can hook up different sensors and things like that very easily to it. The only downside is some of the sensors are analog, and the Raspberry Pi does not have an analog input or output, really. It's got PWM, which isn't exactly the same thing. The Arduino does. The Arduino actually does do analog. And so the sensor kit, I believe, comes with one analog to digital adapter, but you can only have one attached to your Raspberry Pi. And so if you ever try to do anything with multiple analog sensors, you kind of can't do it. And it's kind of annoying. Like, I kind of wish that the Raspberry Pi 5 would have like multiple analog inputs and outputs on it. It should be really nice. Mechatronics is looking at Tinkercad. Cool. Free Pi, please. Can the school send us Pis? No. Basically, they're already kind of overwhelmed checking out stuff. They're all at school right now. I've dropped them back off at the school, but they don't want to deal with it because none of these things are inventory controlled, and they don't want to, like, if you turn this back into the library, the librarians do not want to go through your kit and verify every single sensor is there and working. You know what I mean? They're like, no. They're busy enough as it is right now with all the pandemic stuff going on. Could you go to school and just get it? And unfortunately not. I mean, I guess I could go to school and just like sit in the parking lot like a drug dealer, like pop my hood open. Yo, man, you want some pie? Want some pie, man? I don't know. I'm kind of tempted to do it. Kind of tempted. I don't know. Is everybody in Fresno? Like, would you even have a way of getting a pie? I know some people like walk or just went to like Idaho or something. What do you guys think? I'm fine with it, I guess. If we could set up a time and a place to meet up. The trouble is, if any of you guys don't have access to the campus, then Watson's not in Fresno. Yeah, alright, well, I guess we could check them out on Thursday and then take them back 2 weeks later, something like that, if you guys want to. Watson has a few pies already. Alright. Well, how does that sound to you guys? Like on Thursday, we could meet up at like 11 on Thursday. And then, yeah. And then 2 Thursdays later, you can bring him back. Does that work? You guys want to do that? Okay. So I'll make an announcement on Canvas. I'll be there from 11 to 11:45 because I got to get back home to stream. And then I'll hand out Raspberry Pis to you guys in the parking lot. So, I'll be a pie dealer, yeah. So, let me show you where I will be. It's the wrong close community college. No. Yeah, it looks like this. Okay. I'll be right here. Okay. So there's a flagpole here. If you just try coming to the flagpole, you'll see me like right over here. Okay. So I'll make you live in Sanger. It's not too bad. It's not too bad. Yeah, just drive to the flagpole on campus, and then you should see me off to the side with my trunk open with some Raspberry Pis in it. Hopefully this will work out. I do kind of want to do a project with you guys, so. Does that sound good to you guys? That'll be, I don't know, something. Where most of the admin parking lot is at. Yeah, this is all teacher parking over here. My classroom's kind of over there, so I'll just wheel it out. Okay. When it'll be Thursday at 11 to 11:45. We're by Singer today, but this is until Thursday. Unless Wheeler, you want to come by my house, I've got some pies here. So Wheeler, come by my house, and if you're going to Singer later on, we can arrange transportation. I see. Okay. So, and then 2 Thursdays from now, meet up, finals week, drop them back off. And we can do like one project or something like that. Okay. Does that sound good to you guys? It'll be a little bit of a hassle, I guess, to kind of arrange all this, but it's fun. Physical computing's fun. And I've been kind of sad you guys haven't been able to do any of it, so. Okay. All right. So I'll make an announcement. 11 to 11:45 on Thursday. I'll be here, parking lot A, next to the flagpole, and I'll just have a briefcase full of pies, handing them out to people. Sensor kits, super kits. There's a certain chance that it will not work, so I might give you 2 pies just in case, because sometimes students will like reformat the SD cards and things like that. So they won't work out of the box, things like that. Do you have an Raspberry Pi 3? Yeah, that works. But you'll need to have sensors and motors and things like that. Okay, you get a taste of Pi. All right, so that's it for today, guys. This was our introduction to Physical Computing Day. I'll read through your code tennis assignments and your bus worksheets, and see you guys in real life for the first time for some of you on Thursday, 11 to 11:45. All right, peace out.